Hello, I welcome you all in this presentation related to the subject failure analysis and prevention. And we are talking about the failure analysis of steel components, and in this particular presentation we will be talking about the failure analysis of a component which failed due to the faulty case hardening heat treatment and secondary processing. Okay. So, in this presentation, first of all, we will try to understand the various approaches, methods which are used for the case hardening, and also the special heat treatments which are carried out for better manufacturing, for improving the performance. Okay. So, as far as the content is concerned, in this presentation, we will be talking about the stress relieving heat treatment. Okay. During the manufacturing and during the heat treatment, variety of the heat treatments are during the manufacturing process like casting, welding, forming, lot of heat treatment, a lot of residual stresses are induced. So, it is good to relieve the residual stresses to improve the performance. So, the stress relieving heat treatment we will be talking about first, and then in process annealing. This annealing is primarily done for inducing the ductility in course of the rolling or the forming processes which are done under the cold conditions, so that the desired ductility can be induced. So, basically the rolling wire drying kind of the processes where things are done in the lot number of stages. So, after the initial stage materials get hardened. So, to induce the softness, the in process annealing is done, so that the material can be formed continuously without development of cracks. Case hardening is one where the surface layers are hardened, while the core properties or the properties below the surface are maintained or they do not get affected. And this is especially needed when we want one set of the properties in the core, say this is core, and at the surface we want a different set of properties. Okay. So, in this case we want the case hardening heat treatment. So, a range of the case hardening heat treatments are there, which are simply based on the heat treatments or controlled plastic deformation or modifying the composition of the steel surface layer, so that the desired structure and properties can be induced for developing the desired set of the properties. Additionally, we will be talking about one case study where the faulty case hardening heat treatment followed by the machining led to the failure of the crankshafts. Okay. So, and also the relevant failure analysis observation and findings will be covered in this presentation. So, starting with this, the special purpose heat treatments are like stress relieving heat treatment, in process annealing for, so this is for reducing the residual stresses, this is for inducing the ductility, percentage elongation, okay, and reducing the hardness being introduced due to the work hardening, and the surface hardening or case hardening heat treatments are done like these are the three approaches. One is where only controlled surface layer deformation is achieved using methods like friction stir processing, burnishing, okay, short peening. So, these are the methods where controlled surface layer deformation is used for enhancing the surface properties, and then controlled heating and cooling like in case of the laser hardening, flame hardening, induction hardening. So, these are the methods which are particularly applied for the high carbon hardenable steels. Okay. So, that the controlled heating and cooling gives the increased surface layer hardness for improved wear resistance, improved the tensile properties, improved fatigue properties. Okay. Third method and third approach here is like composition of the surface layers is modified. Okay. These are the surface layers. So, up to certain depth we will be introducing the unique elements near the surface layers. So, they form their either compounds or they help in achieving the desired phases near the surface layers in order to modify the properties, while the core remains unaffected. Okay. So, that is the approach of the compositional modification for controlling the surface properties through carburizing, nitriding, cyaniding, aluminizing, boronizing. Lot of other approaches are also there depending upon the element which is being introduced in the surface. for achieving the desired phases and desired properties, a different kind of the surface modification methods are there by changing the composition. And we will be taking up one case study related to the faulty heat treatment or the incorrect case hardening heat treatment followed by secondary processing. So, as far as the stress relieving is concerned, whenever a component is subjected to the localized heating, localized plastic deformation, so then this, whether it is casting, welding or forming, this leads to the development of the residual stresses. Residual stresses are those stresses which are present in the component without application of external stresses. So, if the residual stresses are tensile in nature, then they compromise residual tensile stresses, they compromise their ability to take up the tensile load or ability to sustain the fatigue conditions of the tensile type. So, the fatigue resistance and the static load carrying capacity under the tension is compromised when the tensile residual stresses are present. When under the conditions when either localized deformation is done or when the localized heating and cooling is done. Okay. So, this will be leading to the development of the residual stresses. If those residual stresses are tensile, then they will be adversely affecting the performance of the component under the tension. So, what we do? We try to either induced using other methods, try to induce the residual compressive stress, so that the performance of the component can be enhanced and the adverse effect of the residual tensile stresses is neutralized. So, what is done? This is the temperature range. You see, the component is subjected to the heating below the lower critical temperature, so that the locked in strain resulting in the residual stresses can be eliminated. So, this is one heat treatment approach. The heat treatment which is done for relieving the residual stresses is called stress relieving heat treatment, and temperature for stress relieving heat treatment can range from say 200 to the 700, that is below the lower critical temperature, so that the residual stress magnitude can be minimized. Maximum residual stress magnitude can be equal to the yield strength. Okay. So, when the exposure is given, say in x axis we have the temperature, here say 100, 200, 300, 400, 500, 600 like this, and it can go up to say 700 usually, and here we have temperature at which the exposure is being given. So, here in this side residual stress, the maximum magnitude can be equal to the yield strength. So, say 100% residual stress, then 80%, then 60%, 40% residual stress left, 10% and 20%, say 10% and 0%. What happens when the exposure is given to the low temperature, the residual stresses are high. So, say no exposure means the residual stresses will go like this. So, when the exposure is given say for 1 hour, then residual stress come down in this way. Okay. Increasing temperature means reducing the residual stress. How much? 80% of the yield strength, 60% of yield strength, 40%, 20% and 10% of the yield strength. So, that is the left out residual stresses due to the high temperature exposure. It may be absent also, it may be completely relieved. So, what happens when the temperature is increased, yield strength of material comes down, whatever locked strains are there, they get relieved, and so the residual stress is relieved. Okay. This is one case. So, when the exposure is given for longer time, then how we can see its effect? That is what we can see in the form of another line. So, this is for 1 hour. Say if exposure is given for 2 hours, then it will be going like this, means greater reduction in the residual stress will be happening for same exposure of the same temperature of exposure, say. So, if this is the 200 degree centigrade is the temperature, so this is the drop at after 1 hour, and this is the kind of drop which will be taking place after the 2 hours of exposure. So, it is important not just the temperature, but the time for which the exposure is being given is also very crucial for stress relieving. longer the time of exposure at a given temperature, greater will be the relieving of residual stress. So, if the heat treatment is not done properly, then there is a possibility like lot of residual tensile stresses are left and they will compromise with the performance of the component. Okay. So, it is very important to select the time and temperature for residual stress relieving. This is what we can see directly, the effect of residual stress on mechanical performance of the component. Okay. So, say there is a permissible limit up to which the component can be subjected to the stresses, and say maximum limit without any factor of safety, it will be the yield strength, beyond which it will deform. Okay. So, here it is the combination of like applied stress plus the residual stress. If the combination of these two is equal to the yield strength, then material will fail, it will deform. Okay. So, if we have the higher residual stress, then applied stress magnitude can be reduced, will be reduced. Okay. So, given applied stress is say this much, that is equal to the sigma y. So, when residual stress is 0, means the externally applied stress can be as high as yield strength theoretically. If we apply factor of safety, then accordingly our externally applied stress will be reduced. But just right, if we try to understand the effect of residual stress, then we can see is directly increasing the residual stress will be reducing the externally applied stress. So, maximum magnitude of the residual stress can be equal to the yield strength, and thereafter we cannot apply, you see, in this stage we cannot apply any externally applied stress because it will material will tend to deform immediately. Okay. So, it is important that for increased ability of the component to take up the service loads, higher service loads, it is important that like sigma r, if sigma y is equal to sigma r plus sigma a, that is the applied stress, then to have the higher value of the sigma a, that is externally applied stress, sigma r must be low, and this can be done through the stress relieving. We need to eliminate or minimize the residual stresses as much as possible. Now, we will be talking about the three different types of the methods which are used for improving the surface hardness. So, the one method is the flame hardening. This is particularly applied in case of the high carbon, like say greater than 0.5% carbon, okay, high carbon steels having high hardenability. Okay, this is the prerequisite, high hardenability. So that on heating, you see this is the surface, when heat is applied through the suitable heat source, it can be induction, it can be laser, it can be flame, anything. When the heat is applied, near surface layers are heated to the austenitic state, that is the above the upper critical temperature. So, that near surface layers get austenitized, followed by, you see, the heat source will be moving, followed by the jet of water. So, that austenite is cooled rapidly to transform the austenite into the martensite and enhance the surface hardness. This is the logic. Transformation of austenite into the martensite will be easier when the hardenability is high, and this is particularly when the carbon content or carbon equivalent is greater than 4.4, carbon equivalent is carbon content is greater than 0.5. Okay. So, this is one typical example where the surface hardening is being done through the flame. Okay. So, there is a flame, oxyacetylene flame is used for the heating the substrate. Say this is a zone which is being heated and heated to the temperature of upper critical temperature, so that the austenitic state can be achieved, followed by application of the water jet, so that rapid cooling of the austenite transforms the austenite into the martensite, resulting in the high hardness. Okay. So, idea here is to increase the surface hardness, so that our wear resistance is enhanced. This is the another approach of surface modification, where controlled surface layer deformation is used for enhancing the surface properties and inducing the residual stresses as well. So, what happens in this case? Say this is the surface layer. So, we will be deforming the surface layer in controlled way plastically. So, this plastic deformation used with the help of a roller, that is a burnishing tool, which is forcefully rolled. See, the burnishing tool is pressed and traversed across the surface. This component is subjected to the rotation just like in turning, and then burnishing tool is pressed against the rotating tool. So, what happens? Surface irregularities get collapsed, near surface layers get elongated, surfaces get smoothened, and surface plastic deformation of the near surface layers induces the residual compressive stress. So, this burnishing surface layer deformation does multiple things. You see, the one, controlled plastic deformation, which causes work hardening or strain hardening, which in turn increases the hardness. This is one. The second is the structures, usually structure gets refined, okay, and elongated in particular direction. Okay. And third is residual compressive stresses are also induced. Residual compressive stresses are induced in the at the surface. So, this is what we see. Turned surface may have high residual stress of positive, that is the tensile type, okay, near the surface layers, but when burnishing is done, it induces the compressive residual stresses, and it also, so you can see up to the 300 micrometer depth, this surface layer modification is observed, that will be leading to the variation in the residual stress level. Likewise, the short pinning is also done. So, in the case of the short pinning, the surface is this, and the steel balls are directed at very high speed, say steel balls of say 2 to 3 in diameter, directed at like say high speed of 500 meter per second. So, they are directed at very high speed towards the surface, where the impact will be leading to the uh, formation of impression, and this impression will be like this. So, this kind of the impression formed or the surface, this leads to the surface layer plastic deformation. That is what we can see here. Due to the impact of the shots, this kind of the geometry is formed. Okay. So, there is a zone at the surface which is plastically deformed, and below that there is elastically deformed zone. So, elastically deformed zone tends to regain its dimensions, and that in turn sets the residual compressive stress at the surface. Okay. So, it is not the plastic deformation which is setting the residual compressive stress, it is the elastic deformation of near surface layers is responsible for development of the residual compressive stresses. At the same time, this plastic deformation, of course, it will be causing the strain hardening, that in turn will be increasing the hardness. So, the short pinning will be doing the two things. One, you see, increased surface hardness due to the strain hardening occurring due to the plastic deformation of the near surface layers, and development of the residual compressive stress. So, these two things are very much favorable for enhancing the performance of the component under the tension and under the fatigue conditions. Friction stir processing is the another solid state method which is used for modifying the surface layer properties. So, the approach is shown here. Initially, the component may have the structure like this, where the constituents are coarse one and they are needle shaped. So, the coarse constituents with the needle shaped geometries, they offer very high stress concentration at the tip and edges. So, because of the stress concentration at the tips and at these edges, our load carrying capacity is compromised. Coarse and sharp edged needle shaped component, needle shaped constituents, these two reduce the percentage elongation, that is ductility, these reduce the toughness, okay, these reduce the strength as well. Okay. You may get the higher hardness, it is fine, but because of the coarse structures and the fine needles, they adversely affect the mechanical performance in general. Okay. So, what if you want a very good combination of the high hardness and the good ductility and or the improved properties at the surface, then what is done? Near surface, let us say this is the component with a lot of coarse grains, okay, like this needle shaped structures. So, what we do, using the suitable FSP tool, say this is the shoulder and this is the FSP tool pin, and this will be rotated, plunged rotated, planched and then traversed across the surface. So, all these coarse constituents are broken down and they get refined. So, that is what we can see, these big and needle shaped structural constituents, they get refined up to certain depth depending upon the tool pin depth. Below that, the structure will remain unaffected. So, this is what is done actually in case of the FSP. This is the tool, this is the shoulder and this is the pin. Okay. Pin is planched and rotated, and so in one pass it will be covering, like say in the top view, if you see the pin is here, the entire zone will be covered, then the pin will be inserted here, then another zone will be covered. That is how the number of passes are given. These passes most of the time are the overlapping. So, that is why it happens in case of multi-pass friction stir processing. This multi-pass friction stir processing helps to cover the entire area. That is what we can see here. This is showing the number of like say 7 passes to modify the surface properties of this halva, just for an example. And when the FSP is done, you can see the structure gets completely refined. Many times in case of work hard naval metals, it helps to increase the hardness as well. Okay. But in case of the precipitation hardening metals, precipitates get lost and we may get the reduced hardness as well. So, this is what we can see, there is great similarity in these structures, structure get refined. Okay. If we consider the transformation hardenable metals, then in that case not just the refinement will be happening, but the soft phases like ferrite, perlite and ferrite, they will form the hard constituents like martensite, and the formation of the martensite will be resulting in the increased hardness and increased load carrying capacity. Okay. So, this is the another solid state process. So, if the FSP is not done properly, then of course, it can lead to the properties that we do not want. Okay. This is the another approach where the surface properties are modified by changing the composition of near surface layers. So, say there are variety of layers, we can introduce number of constituents, like we can introduce nitrogen for nitriding, for boronizing, boron for boronizing, aluminum for aluminizing, silicon for siliconizing, carbon for carburizing. Okay. This is a substrate. So, when we provide a particular element rich environment at the surface, at a high temperature, these diffused elements, they can work in two ways. They can form solid solution, okay, one, or they can form some kind of the compound through the reactions, okay, or they can help in forming certain kind of the phases which are of the desired properties. So, that is what is done in carbon. In carburizing, carbon is enriched in the low carbon steels, and then that helps in forming the high carbon martensite. Okay. In low carbon steels, carbon content may be very low and may not be able to form the martensite. So, carbon is enriched at the near surface layers, followed by the heat treatment, that will be producing the high carbon martensite of the desired hardness. So, most of the time the trend goes in like this, where at the surface layer the concentration of element will be high, and on increasing depth from the surface the concentration will keep on decreasing, and below certain level there may not be any presence of the elements that we have enriched at the near surface layers. So, substrate will remain in that case below surface layers, the component or the substrate may remain unaffected. This is the approach. What we do, carburizing is one of the most common, carburizing and nitriding are the two most common surface modification approaches, where in carburizing, carbon content is enriched in case of the low carbon steel components having say carbon less than 0.2%. So, what is done? The steel component is heated in the carbon rich environment, then carbon content is enhanced in the near surface layers through the pack carburizing, gas carburizing, etc., or liquid carburizing, and then it is cooled. Okay. Then after cooling, again the component is heated again in case of pack carburizing, that is solid carburizing, and then after reheating to the austenitic state, it is subjected to the quenching. So, the first stage in case of the carburizing, especially pack carburizing, is the carbon enrichment. Second stage is about the hardening heat treatment. Okay. So, reheating to the austenitic state followed by rapid cooling, that is the quenching, so that the whatever carbon has been introduced at the surface layers, that can be used to transform the austenite into the high carbon martensite. Okay. If anything goes wrong here, then the desired set of properties will not be achieved. This carburizing is done usually in the high temperature range of, like, say, 800 to 1000 degrees centigrade. Okay. So, this high temperature is another problem because it will be modifying the substrate properties. Nitriding is another process which is a low temperature process. Low temperature means because it is done around 500 to 600 degrees centigrade in the ferritic state, when the steel is in the ferritic condition. So, what is done? Carburizing is done in the austenitic state, while nitriding is done in the ferritic state. So, it needs lower temperatures. So, what is done? Nitrogen near surface layers is introduced at this temperature. So, near surface layers get enriched with the nitrogen. Then in case of carbon steels, it simply form iron nitrides. But iron nitrides may not be very effective in enhancing the surface properties. So, what is done? We choose the steel in such a way for nitriding purpose that it is having the desired alloying elements for forming the strong hard nitrides like chromium, vanadium, tungsten, these kind aluminum. So, these are the kind of elements. See, steels having these elements, they will be interacting with the nitrogen effectively and forming their nitrides to enhance the surface hardness and modify the surface properties. Okay. So, but the important thing to be noted is, like, this is the low temperature treatment because it is being done 500 to 600 degrees centigrade. Low temperature means it will take long to diffuse the nitrogen up to the desired depth in the desired concentration, and that is why it is a very long process. It takes tens of hours and maybe even above the 100 hours. So, process, since it is being done at the low temperature. Okay. So, the good part here, due to the exposure at the low temperature, is the substrate properties are not compromised because things are below the at the low temperature, and distortion tendency is also minimized, cracking tendency is absent. Okay. So, these are the elements which, if they are present, they will be helping a lot in enhancing the effectiveness because they are strong nitride formers. They form hard and strong nitrides. This is what happens in case of the carbon steels. When only iron nitride is formed, the increase in hardness is limited. But when we have nitriding steel having the desired chromium, vanadium, aluminum kind of the and other molybdenum alloying elements, then they form very hard, stable nitrides which are good actually for enhancing the surface properties and the hardness. Okay. That is why we get very good and effective results when the steel is having certain strong nitride forming elements. This is what happens when the nitrogen concentration is enhanced. At the surface, nitrogen concentration is very high, and that is what we will be seeing one kind of the needle shaped nitrides, gamma nitrides little below that. So, in both these cases, nitrogen will be forming certain kind of the compound, and below this, further below this, the nitrogen will be there. There will be another nitrogen diffused zone. Okay. Now, we will have case study related to the crankshaft. So, crankshafts are subject there. This is a very critical component in many engineering systems. Automobile is very common because this crankshaft helps in converting the reciprocating motion in the rotary motion and vice versa. These are subjected to the fatigue. This is one. So, for the fatigue conditions, there should not be any kind of the stress concentration. There should not be defects, because these will form the weak zones for easy nucleation of crack, their growth, finally sudden fracture. Okay. So, these are the three stages: nucleation, growth and sudden fracture. If a component is having stress razors or the defects, then it does not require nucleation stage. The cracks, means the defect, crack like defects will start growing directly. Okay. That is why the fatigue life is significantly less. So, the crankshafts fail primarily due to the fatigue one, and then especially these, the failure tendency extremely high when there are stress razors. Stress razors may be in form of defects, discontinuities or machining irregularities in high stress areas, or the assembly of the crankshaft is not perfect and having the misalignment that will be causing the skewed loading. Now, we will be taking up one case study wherein the failure analysis of the crankshaft will be taken up. So, the crankshaft of a 4-cylinder engine failed prematurely, and crankshaft failed prematurely within the 2 years of service, which should have worked actually more than 10 years. When investigation was conducted, it was found like alloy steel composition was there as specified. So, material is perfect. Okay. Design is also as per the recommendations. So, there is no design issues as far as geometry and dimensions are concerned. Visual examination showed that the component that the crankshaft shows worn out zones, means the wear was one of the mechanisms that led to the failure. The mechanical property study suggested the lower hardness 700 as compared to the specified 740 HV, and the microstructure showed the normal structure at the core as expected, but the very thin layer of the nitride zone, because the crankshaft was subjected to the nitriding and the thickness layer of the modified zone was less than 20 micrometer than the specified 120 micrometer. So, the crankshaft surface was modified to just 20 micrometer rather than specified 120 micrometers. So, the case hardening was not proper. The modification of the surface was not up to the desired depth. There was a the crankshafts after this modification were subjected to the grinding, and it appears like over grinding was done, that was a possibility for removal of the hardened layer and resulted in the significant reduced modified depth of the crankshaft. Okay. So, here further investigation was done and it was found like there was no defect whatsoever that can be attributed as a reason. Only issue was there very thin layer of the modified zone, surface modified zone. Okay. There is a possibility of very thin layer that nitriding was done for very thin layer up to lesser depth, or during the grinding it was removed. Operation was done at a higher speed than the normal one. This was another reason which was identified. There was no proper lubrication. So, the deficient lubrication was another reason. So, if we summarize this, so the hardness was low, okay. The case depth was less than the specified. The speed of operation was high, means the relative speed was high, and the lubrication was not proper. So, all these conditions led to the wear of the crankshaft. Additionally, the stereoscopy and scanning electron microscopy suggested the presence of craters, pits and abrasion marks indicating the wear, and comparison showed that lower hardness, thinner hardened layer as compared to that of the new one. So, these observations suggest that the crankshaft failed due to the lower hardness, poor maintenance in form of improper lubrication coupled with the improper nitriding not up to the desired depth, and improper grinding, possibility of removal of the nitrided layer during the grinding operation. So, here I will summarize this presentation. In this presentation, basically I have talked about the various approaches which are used for the modifying the surface properties. There are 3 categories of the surface modification properties, where one is just heating and cooling is applied for modifying the surface properties like flame hardening. Then we can also do only the controlled surface layer modification through the controlled deformation up to certain depth using methods like burnishing, shot peening or FSP. Then surface properties can also be enhanced by modifying the surface composition by introducing suitable elements. It may be carbon for carburizing, nitrogen for nitriding, or it can be combination of carbon and nitrogen both for cyaniding, like boronizing, aluminizing, siliconizing, there are various other processes. And additionally, we have also talked about one case study related to the failure of crankshafts, where it was found that the lower hardness, lesser modified depth of after nitriding, and the absence of lubrication due to the improper maintenance, and all these led to the wear of the crankshaft that led to the failure. Thank you. very much.